Thank you. Yeah, so today we're gonna talk about how dataset and DataFrame, how they implement it, what's the difference, what's the performance difference, and how we bridge the gap between dataset and DataFrame. So we're gonna talk about how we use Spark at Apple a little bit, and then we're gonna talk about Spark SQL, the overview of the Spark SQL, the basic idea, how Catalyst engine work, and so that we have enough knowledge to cover the rest of the material. And then we're gonna talk about dataset, DataFrame, some example. And then Anton gonna talk about how we optimize the dataset using bytecode analysis so that we can bridge the performance gap between two implementation, two APIs. Okay, so Spark at Apple. So as you guys know, data is important and data is really useless unless we can find insight or iterate on top of the data to find something meaningful quickly, as quick as possible. So at Apple, many teams, such as Siri, we choose to use Spark as data processing engine. We use it to process the data, clean up the data, do machine learning. So it's really useful tools we are using at Apple. And we also have a team working on providing Spark as service, infrastructure service. So they build a scalable service that can scale up the Spark cluster on demand. And also the framework is disaggregate architecture, meaning that the storage and computation are separate. So whenever you want to scale up the computation, you can put more computational resource into the cluster. And whenever you need a more resource in terms of storage, you can scale up in the storage side. It's two separate systems. And we have over more than 1 million executors running every day. So imagine how big scale is it running Spark at Apple. Okay, so talk about Spark SQL a little bit. So in Spark SQL, one of the most important concept is Catalyst Optimizer. So how does it work? So Catalyst Optimizer gonna take SQL expression, the SQL query, or even dataset query or DataFrame, and then we're gonna translate into unresolved logical point. So in unresolved logical point, the attribute or the type name is not actually resolved yet, but Spark gonna combine with the catalog and do the analyze, and then we're gonna get a resolved logical point. So over there, we already have the attribute name, we have the data type, the type checking over there is already done in runtime, and then we're gonna run optimization on the logical point. So how you work is actually the logical point look like a tree structure. You have left node, and bunch of operation chain on top of that, so it's a tree structure. So the way we optimize the logical point is, since it's a tree structure, we recursively traverse the tree, and then using the pattern matching to find out the better rule and replace the rule in the tree, in the logical point. So we do it until the logical point won't be changed, so stabilized, or until we reach the threshold. And then we do physical planning. So combined with the physical information, we can create a bunch of the physical plan, and we use cost-based optimization to pick up the best physical plan. And then we do code generation. We generate a specialized code and execute it on top of the data. So this is the overall picture, although it's oversimplified it, but it's an overall picture of how Spark Catalyst Optimizer work. So then we can talk about a little bit dataset and DataFrame. So yeah, so I would like to do a quick survey before I talk to more material. So how many people over here are using dataset? Wow, quite a lot, more than half. And how many are using DataFrame? Okay, even more. Okay, good. You guys are doing better. And who didn't raise your hand? Okay, a few. So why are you guys here? You guys using RDD? Come on, it's so old. Or come here to learn Spark? Okay, it's good. Okay, then let's talk about DataFrame. So DataFrame is actually So DataFrame is an untyped relational API we introduced in Spark 1.3. And from Spark 2.0, DataFrame is actually dataset of row. And what is row over here? The row over here is actually an object that doesn't have a specific encoder. So there is no specific encoder, so it's not a case class, it's just a row object. So there is no, encoder over here. And dataset is actually DataFrame or dataset plus an encoder. An encoder can be something you implement, can be a case class, which means encoder can be used to translate the internal Spark data structure into the case class, for example. So dataset is kind of like, DataFrame similarly. So basically, dataset provides all the API DataFrame has plus untyped plus type API. That because dataset has encoder, which means you can convert it into the type API. Okay, so let's talk about some of the examples. Let's say we have real estate information, we have address, facts, school, so we have some data like this, and it's a data frame. So let's say we want to do a really simple query. We want to find out all the house that has the price more than $2 million, for example. And because of the rich people, is worrying about bad guy gonna go to their house. So let's say we want to replace the street address by UUID. We hash it out. And also we respect privacy at Apple. So basically, this is a really traditional query that we just replace the street address by UUID, and we query all the house that has larger than $2 million. So the execution plan is how Spark actually executes this plan. So here is the execution plan from the previous query. And as you can see, we have data filter that filter out the price larger than $2 million. And over here, we did a projection to create a new street address with UUID. So it's being replaced. But the most important thing we want to look at is that in the original query, we replace street address by UUID first, and then we do the conditional predicate later. However, Spark is able to find out, we never touch price at all in the query. So basically, because of the data is not being touched, so you are able to push down the predicate earlier before you do the computation or doing the UUID computation. So what's the nice thing about that? For example, if you have really expensive operation over here, for example, it's pretty cheap just doing UUID. But let's say you have really expensive computational operation over there. What's going on is that you're gonna execute it over and over again for each record. If you don't have predicate pushdown or predicate, if the predicate is not pushing through, you're gonna execute it every time, and then you filter them out, most of them. So basically, Spark is really smart to avoid extra computation by pushing the filter earlier. Then you don't need to do a lot of data reading and also extra computation. And that's how Catalyst help us in the optimization rule. And let's look at the dataset, how dataset work. So this query is identical to what we did previously. So we just, is a dataset. We get a concrete object of home project, and then we replace the street address by the UUID, and then we do the filter later. It's identical to the previous data frame query. So look at how it works. Although you may argue this looks simple, and you can have a concrete object easier, but let's look at the execution plan and see how Spark actually executes this code. So first of all, Spark gonna read the data from bucket. And then Spark gonna deserialize it into an actual POJO object over here. So we're gonna create a new instance of the home. And then we apply the Lambda function, which is defined over here. So basically, we are copying the home object and then replacing the street address. So here we apply the Lambda function. And Spark has to do it because from Spark internal data format, which is being read directly from Parquet, we need to convert it into POJO so we can execute the Lambda function. So there's the cost over here. And then you apply the filter function, which is also another Lambda function. And then finally, we need to serialize it back into Spark internal format so that Spark can do further further execution. So look, this is so expensive. You look at all the condition and then convert it from POJO and put it back to Spark internal format. So the whole flow is really expensive. And more importantly, all the Lambda function here are opaque to Spark. Spark doesn't know what's going on inside the Lambda function. Spark cannot do anything. Spark cannot optimize it. Spark doesn't know, oh, this filter can be pushed earlier because this filter is filtered on some column that hasn't been modified yet already. So Spark cannot do that. That means all the map Lambda function has to be carried out for the entire data set. Instead of like push the filter earlier, so we filter out most of the data and then we do the computation. So that's why it's so expensive, so slow, because the problem is that we have deserialization plus the catalyst optimization cannot be done in the dataset framework. But why people still like, a dataset? Because it provides a lot of benefit to people. It's a type API. It's guaranteed a schema consistency in compile time. It's good. And also, it's easier to exchange the code between Java, Scala, between like a dataset API. I believe many people, including like us and Apple, we use some of the library that developed by other team written in Java. We inject it into the Spark, into the dataset API. This is something people do every day. Dataset is easier to do that. We can share libraries, Scala library, Java library, here, there, it's easy. And also, dataset has compile time exception. The schema is being checked in the compile time, and that also increases the data scientist productivity because analysis is done in compile time, not in the runtime. So you can see the error earlier instead of like, you type something in the runtime and oops, it's not working, like Python. But what is the drawback for using dataset? Dataset can be 2 times up to 40 times slower in many of the cases compared with DataFrame. And here is the benchmark done by open source community. And as we mentioned before, dataset has serialization and deserialization costs that require converting the Spark internal format into POJO in order to apply the Lambda functions. And because many of the POJO are created for each row when you process the data, and because of that, we're gonna have a lot of GC pressure. We create a bunch of objects and we immediately, put them into the garbage collector. So it's creating a lot of GC pressure as well. And also, with the data set, as we shown before, it's not able to apply catalyst optimization because it's opaque to Spark. Spark doesn't know what's going on. Spark can just execute all the Lambda function provided by user. So there's no way Spark can arrange the order and see, we can reduce this optimization, reduce this execution at all. So this is a big problem for dataset API. So now Anton will talk about like the solution and the approach we have to tackle these problems and how the problem help us and how the performance difference with our improvement on this area. Thank you.
Cool. Thanks a lot, DB, for explaining the trade-offs of different APIs in Spark SQL. Now I think users have enough information to make a wise decision which API to use. The rest of the talk will be pretty technical, so we will talk about how Spark can actually speed up data sets. And as you might already guess, the idea is to leverage bytecode analysis. This will help us to replace user closures that are basically black boxes to Spark with Catalyst expressions that it can understand and therefore can optimize. And moreover, we can avoid the need to convert data from the Spark internal format into JVM objects. And this idea was originally suggested by Reynolds. However, it was never implemented in the open source Spark. And there is no progress for more than 2 years. Recently, we decided to give it another try at Apple. We picked some of the ideas discussed in the community, but we came up with a completely different implementation that also has a bigger scope. Before diving into details, I will walk through some basic concepts that we need to understand in order to follow the rest of the talk. And first of all, we need to clarify what bytecode actually means for people who are less familiar with JVM-based languages. Bytecode is a set of instructions that is supported by JVM. And compiling a Scala or a Java program actually means taking its source code and converting it into bytecode that can be executed by JVM. And bytecode is platform independent, which allows us to run our Scala and Java programs on multiple platforms. We also need to understand the architecture of JVM and what components it has. And apart from the heap, we also have other areas. For example, metaspace stores metadata about our classes. In particular, it stores per-class structures such as runtime constant pool, data about your fields and methods, as well as code for methods and constructors. And we will rely on that information for the conversion as well. Also, every JVM program has at least one thread, and every JVM thread has its own private JVM stack. The stack stores frames, and every time we call a method, a new frame is created, initialized, and pushed onto the stack. Whenever the method returns, that frame is popped from the stack. And the JVM stack cannot grow infinitely, so it has finite size. And for example, if you have a recursive method that never terminates, then you will end up with Stack Overflow error at some point. What is also very important to understand is that each frame is independent. It has its own array of local variables and its own operand stack, as well as a reference to the constant pool. And we will need both, actually, all those three components to do the conversion. So you can see that instructions within a particular method describe which operations you need to perform on the operand stack and the local variable array of that particular frame. And every closure that we use in Spark actually is represented as a method call, which will get its own properly initialized frame. Let's consider a quick example. So we have a trivial static method that accepts an integer, increments it, and returns the result. And we are calling this method with 5 as our argument. Below you see the generated bytecode. In total, you have 4 instructions. And you also have some metadata around this. You know the number of local variables. Also, you know the number of arguments that you have. They both 1 in this case, because this method is static. And also, you know that the maximum size of your operand stack will be 2, which means that you will have at most 2 elements at the same time. Whenever you call this method, a new frame will be created, as I said, and the operand stack will be originally empty. In this particular use case, the local variable array will look like this, because the passed argument, which is 5 in our case, will occupy the slot at index 0 in the local variable array. If we interpret this line by line, then the first line will tell us to load the value at index 0 in the local variable array and push it onto the stack. And after this step, we basically have 5 at the top of our stack. The second instruction will tell us that we need to load an integer constant of value 1 and push it again to the operand stack. So after this step, we have 2 elements on top. And the third line will actually tell us to pop 2 elements from it, like the top 2, and add them together because they are integers, and push the result back. And finally, the last line will tell us to pop the top element and return this as a result of our computation. So this is basically what happens when you call a method like this. And if we come back to Spark, then we have multiple approaches to derive Catalyst expressions. So first, you can translate the stack-based code directly, which means you will iterate instruction by instruction, simulate what happens to the operand stack, and this will give you the result. And this is exactly what we did just now. And another approach might be is to convert your bytecode into a format that's easier to understand and easier to work with. You might build an abstract syntax tree, or you might use some format like Jimple or something like that. The second option really makes sense if you want not only to translate your expressions, but also if you want to optimize them later on. It will be much easier with that. But in our particular use case, we just need to translate, and we expect that the Catalyst optimizer will do the rest for us. We went for the first approach during our proof of concept, but we keep this question as open. So we're still thinking about if there is some intermediate format that would make sense for us. Next, let's take a look how typed operations are actually handled in Spark. So for example, we have a data set created out of a range of long values, and then you have 2 typed transformations on top of it, 2 closures. On the right-hand side, you see the logical plan that's generated for this. And what is really important to understand is every typed map transformation is actually represented as 3 nodes in your logical plan. So first of all, you have deserializer, which converts data from the Spark internal format into JVM objects. Then you have map elements, which will basically invoke your closure. And finally, you have serialize from object, which will convert the result back into the Spark format. And it turns out if you basically capture those 3 nodes, you probably have enough information to replace that with untyped operation. And the algorithm is pretty straightforward, the one that we did in proof of concept. First of all, you need to get the closure that you want to execute, and also you need to get the bytecode of it. In Scala 2.11, it was fairly simple because every closure was anonymous class, which you knew the name of. Plus, you knew the method name that you wanted to call. The only remaining part that you had to supply is the correct method signature, which is still pretty easily derivable from the metadata around your transformation. Scala 2.12, things got more complicated because closures are represented as Java lambdas. So not possible to apply the same logic, but it's still doable. And in fact, Spark already does this in a couple of other places. But I will not dive into details. So once we know everything about what we want to call, we actually need to build the correct local variable array. And that array has to reference equivalent Catalyst expressions that we will operate on. And this is probably the trickiest bit that you need to accomplish, because here you have to convert your deserializer. That will define your input. And the problem is that deserializer itself can have other method calls, and like multiple ones. And there might be static, there might be calling constructors, as DB showed, and all of that stuff. So first, you need to apply this framework to those methods before you can actually convert your closure. But it's still doable in some of the cases. And then once you have the method you want to call, once you have the local variable array, you actually need to create an operand stack, which will contain those partial Catalyst expressions that you will operate on. Once that is in place, you can follow instruction by instruction and simulate what happens to the operand stack. And once that is done, you can assign the final result to the expected attributes. And here's where the serializer helps, because it knows the expected attributes, their names, their data types, so you can map the result back into what was expected by Spark. All right, let's take a look at another example, which is like more real use case, and what we can achieve with bytecode analysis. We have two case classes, data and nested data, and we also create a data set out of a range of long values as well. This time the range is a bit bigger, but still, I mean, it's a local data set. Then we have the first map transformation that maps primitive long value into a case class. And the second map transformation will map those objects into nested data objects. And alongside those transformations, you actually access fields, you call methods, and you have mathematical operations as well. And finally, after all that is done, you have a filter on top of it, in which you access the leaf column, and you apply a filter on top of it. And here's the physical plan that's generated. So Spark is smart enough. It avoided the serialization and deserialization back and forth in the middle. So it will happen only once. So you first do the deserialization. You convert Spark internal format into the JVM object. Then you have a sequence of type transformations, right? So to type, to map, and then filter. And then you have one serializer that converts everything back to the Spark internal format. And what is important is that those map transformations are black boxes. You really don't know what's going inside them, so you cannot optimize them. And the filter is really executed after those two map transformations. So the same query, but with bytecode analysis, will give us a much simpler and more efficient physical plan. So this is what was actually executed. And we see that Catalyst was smart enough to squash two map transformations into one. They are fairly easy. And also, it knew what was going on in that map transformation, so it could also push the filter, which is a big deal. Even in such a small local use case, it can be like 40 times faster. And imagine if you really need a real data set from remote storage, and you're talking about petabytes, then it might be a big deal for you. So far, so good, but why it's not already there, right? And the point is that it's really challenging, and probably the biggest challenge is that you need to preserve the JVM semantics while you operate in the SQL world. All Catalyst expressions, they have SQL semantics, right? And it's not the way JVM works. For example, null is handled very differently in all of your expressions, exceptions, of course. For example, if you have an object and the reference is null, you call a method on it, it's going to throw an exception, right? So you need to handle that as well. Also, edge cases, like if you divide by 0 in JVM, that would be another exception, for example, in some cases, but not in SQL. Also, the bytecode is very low level, so the result expression can be too complicated. You need to track, for example, the simplest approach to track the number of expressions. If it's too complicated, just fall back. Also, method calls, there's a variety of them, different types, with different logic, and they, for example, build local variable array in a different way. So you need to know all of that, and you need to handle all of that. Also, creating new objects is pretty complicated. I will walk you through an example that will show some of them, not all of the issues that you might face once you want to do the transformation like this. So we have a case class called data, two fields, very simple, and then we have a function that takes a primitive long value and wraps it into an instance of the data class, right? And it calls to a string on that long value. Seems very straightforward, right? This is what you will get on the bytecode level for this. So it's immediately clear that it's more complicated. So what used to be one line is no longer one line. And for example, you need to take care of implicit things that you really don't see in your source code, like boxing, for example. Also, creation of the objects is not one line, not one command. So first you need to create a reference, push it onto the stack, then you need to prepare all the arguments, and then you call the constructor. And also, you have different method types, as I said, and you need to handle all of them. For example, invoke virtual is pretty complicated because you need to implement method dispatch for this. It's not enough to just know the reference type. You actually need to know the runtime type of your object. It's still doable, so we do this. And all of those are actually supported. And also, you need to understand the complexity of what you can deal with. If you want to actually transform and see what's going on in that boxing method, then you will see that it actually calls another one in which you wrap the primitive long value into the wrapper. And if you look into that one as well, then you will probably see that it's really complicated. For example, you need to handle long cache, right, and things like that. So what we do right now, in order to avoid really too complicated expressions, some of the method calls are actually intercepted. Because, for example, we really know what's going on. We really know the semantics of it. So we can probably intercept it and not really look inside it. But it's in very limited use cases, I would say. So I would like to finish with a short summary. So datasets, they are great. They are meant to be a better version of RDDs, because you can apply still the same closures, which is handful. And you expect more optimization from the Catalyst. And also, they are tape safe. So you have more compile time exceptions. Analysis is done at the compile time, not at the runtime. But everything comes with the cost of performance. And as DB said, closures are black boxes. You cannot really optimize them as much as you can optimize data frames. Bytecode analysis can be used to bridge the gap. However, it's also very challenging. You have to address a lot of edge cases. You really need to know how JVM works. And in some cases, the conversion is definitely not possible. So we are working, or we plan to work with the community again. And we plan to share our proof of concept either tomorrow or on Monday. And we hope that together with the community, we can arrive to something that's reliable and covers pretty interesting use cases. Yeah, that's it from us. Thanks.
Thank you.
Thank you, Anton and DB. For people who came late, there's a Q&A session for the next, I think, like 6 or 7 minutes or so. If you have any questions for them, please line up at either the mic on the far side or the mic over here. Thanks.
Hey. Where can we find the announcement?
Sorry?
You said you were going to announce or share it in a couple of days. Where can we find that?
That will be a public PR to open source Spark. We do believe a lot in open source, so everything that we do, DB does a lot for nested data. So everything ends up upstream.
Yeah, so it's going to be a pull request in the Spark GitHub project.
Yeah, and we'll be glad, like people who are interested, that you take a look and see what are the cases that can be handled, what are not.
Hi. Thank you for the talk. I was a little unclear on the. We had some sample code with a before and after, with and without bytecode analysis, and two pretty different physical plans. What was actually done differently in the actual written code between those, or was that just like the underlying optimizer that was managing that? Right.
So the semantics stays exactly the same, right? But what you actually did is all those operations like deserialize, map elements, filter, they all type transformations, right? Mm-hmm. They really require this conversion from internal format into JVM. And in case of bytecode analysis, you could come up with native Catalyst expressions that really operate on the data in the Spark format. For example, the way, instead of creating a case class, Catalyst has this name struct unsafe, which you kind of, instead of creating a Java object, you create a struct inside Spark, and that is very cheap because it doesn't involve any conversion, for example.
Okay.
And also Spark has something called whole-stage code generation. So everything here will be generated as one function instead of like a multiple lambda expression. So with whole-stage code gen, it's going to be more efficient, and it's going to be specialized type instead of like object type. So we can avoid boxing, unboxing as well.
Okay. So as a developer, you would write the same code either way?
Yeah.
Yeah.
Awesome. Thank you.
So it's just transparent to the user.
Quick question. As an alternative, or maybe like multiple solutions, like have you guys also looked into doing a similar analysis with DataFrame so that you have a compile time type checks?
There was some effort around that, I probably know.
Yeah, I don't think so, yeah.
But to be honest, I don't know the deals.
So one quick question. So what is the cost of the bytecode analysis? Like, for example, if you have kind of complicated closure, would it be possible like the analysis is actually more expensive than the query itself? So do you guys have any heuristic or something to determine whether the analysis is worth the benefits?
Yeah, so we have a couple of ideas how that can be tracked. So for example, you can track either the number of operations that you handle once you do the conversion, because it's pretty cheap because we don't do any conversion in intermediate state, right? So if you probably use a library like something to convert into Jimple or whatever, that would be costly, right? Because you translate from the stack-based expressions into something that's intermediate, and then you do the conversion. So that's going to be costly. We don't do this, so it's pretty cheap. What we need to handle is cases where, as you said, closures are very complicated. And then you can either track the time you spend converting or something like that, or you can actually track how many instructions you handle. And if that's too complicated, just fall back.
All right, thanks.
Yeah, quick question. Yeah, I'm very excited to hear revitalizing this Jira. So my question is, so what is the most typical, most useful case in your workload to use this dataset description? What is the best, most useful case in your workload?
For using dataset?
Yeah, by using this description or this notation.
Oh, yeah. So many data engineer, they prefer to use dataset because they can keep like.
I understand that. So, for example, the static checking or something. But I want to understand. So, what feature is necessary? For example, yeah, you say that several challenges, but what challenge? What capability we need to support your typical or most useful cases? For example, more technical term, if I use get feed or such nested class by supporting a get feed or something.
I think it's very useful when you have this option to kind of write a closure that defines the logic. Usually, or sometimes, it might be easier than an equivalent SQL expression, right? Especially if you work with the nested data. Probably sometimes that's going to be easier to just write a closure, and that will be like 1 or 2 lines. In SQL, it will require some of the work, right? And that's probably one of the examples where this would really help.
Okay.
Hi, we're actually from LinkedIn, and actually internally we're also solving an almost identical problem here. So from our experiences, when we're working on this internal POC, so the biggest benefits we're seeing is, with this kind of bytecode analysis, that actually gives us the ability of, from a dataset type APIs, we're also able to do column prunings down to the, the data reading stage, and also eliminates a lot of the overhead of the intermediate data 30s. So I'm wondering, from the experiences you guys have at Apple, whether you guys also see other potential benefits, with doing bytecode analysis on top of the Lambda functions, in the dataset APIs.
I don't think we thought about this, but we will be definitely interested to hear more and then collaborate with you on this and see if there is anything that we can actually have upstream that will benefit all of us.
Yeah. So another challenge we're actually seeing internally is in cases where you have chained map elements operators, where your type basic keeps changing with each new map elements. And the challenge is, in order to figure out which columns we can actually push all the way down to the table scan operators, sometimes it's kind of difficult to actually figure out that, certain field or method invocations on the topmost map elements, how that correlates to, a, sort of a field or, sort of method calls for the most underlying types, in the bottommost, sort of map elements operators. So I also wonder whether you guys also see this kind of challenges.
It is challenging, correct. We solve it by acting before Spark removes this intermediate serialization, deserialization. Because what's really important is to act at this point, right, where each type map transformation is actually as 3 nodes. Because that serializer, this is what contains the expected Java class. Or actually the map elements contains it, but the proper catalyst schema in the serializer that you really expect out of your computation. So we really transform one by one. So either it's the last one, or or if it's the first one in the sequence, and we do it one by one, and we capture those 3 nodes, and that's enough to kind of keep the expected schema correct. At least we didn't see that breaking, I think.
All right, I see. Thanks.
Yeah, thanks a lot. Cool.
Cool. That's all the time we have for questions now. Everybody please give Anton and DB another round of applause.
Yeah, thanks a lot.